Welcome back to Summarize Science, where we break down fascinating new research. Scientists are designing enormous new detectors to hunt for gravitational waves and dark matter using a technique called atom interferometry. These instruments use atoms as quantum rulers, capable of making some of the most precise measurements ever conceived. But there's a problem. These measurements are extremely sensitive to noise, or errors that can mask the real signal. This paper investigates a key source of noise caused by two things working together: the natural curvature of the laser beams used and the tiny, random sideways jiggle of the atom cloud in each measurement. Imagine trying to measure a tiny object with a ruler that is slightly bent, while the object itself is also shaking back and forth. For future detectors that are hundreds of meters or even a kilometer long, this effect becomes a major roadblock. The researchers analyzed different ways to set up the laser and found a difficult trade-off. One setup, which they call HECN, is very efficient at using the atoms, but it's also extremely sensitive to this jiggle noise. An alternative setup, called LELN, is much quieter and less sensitive, but it's also far less efficient and would require much more powerful and expensive lasers. This puts designers in a tough spot. Do you choose high efficiency or low noise? Just how tough is it? To use the high-efficiency setup, they calculated that the starting position of the atom cloud would need to be controlled at the micron level. Even more challenging, its velocity would need to be stable to within a few hundred nanometers per second. That's like controlling the speed of a snail to the width of a virus. Faced with this challenge, the authors proposed a clever solution. Instead of trying to perfectly control the atoms, why not measure the error and subtract it? Their idea is to use a technique called position-resolved readout. This means that at the end of the experiment, instead of just counting all the atoms, a camera takes a detailed picture of the final atom cloud. The exact shape and position of this cloud contain hidden information. By analyzing the final image, they can measure two key things: the cloud's final center point and how tilted the measurement is across the cloud. The researchers showed that these two measurable values have a smooth, predictable relationship with the noise caused by the jiggle. This allows them to empirically learn the error from the data itself and simply subtract it out, effectively cleaning up the measurement after the fact. So let's recap the key points. Future atom interferometers face a serious noise problem from the interplay between curved laser wave fronts and atomic motion. The most efficient experimental designs are also the noisiest, creating a difficult trade-off. The researchers in this paper proposed an elegant solution: take a picture of the atoms at the end and use that image to learn and correct for the noise. This mitigation strategy could be crucial, as it allows scientists to build the most sensitive detectors possible, potentially unlocking the secrets of gravitational waves and dark matter.